Okay, this is going to be the second video on how to find the volume of a solid using cross-sectional areas. And if you haven't done it, I would definitely watch the first video. The problem that we work in this video will be exactly the same problem as we worked in the first video, with one difference. In the first video, each of the cross-sectional shapes had a square, or was in the shape of a square, and in this video, all the cross-sections will be in the shape of an equilateral triangle. Now, I think it helps to visualize what it looks like, first of all. So possibly your book will give you a sketch that actually shows what the situation looks like. But let's go back and take a look at both the square and this equilateral triangle to see what these look like. So again, in the first problem, we had a square. So let's go ahead and remove the triangle. And in the first video, the square, when you drew a cross-section, looked something like this. When you sketched it, the solid that you got looked like this green object right here. So you found the volume of this green solid using square cross-sectional areas. And that was in the first video. Now in this video, the only difference is the boundary conditions still stay the same, but rather than using squares, we're going to use equilateral triangles. Now first of all, let's visually take a look and see what that's going to look like. So instead of a square at each cross-section, let's go ahead and replace that with an equilateral triangle. And that equilateral triangle will look like this. So all the sides are equal length, and it winds up looking like this. Now, what effect does that have on the shape? Well, let's remove the square, and we'll take a look and see what these things looks like. So if I take the square out, and I've got this. Now, this is what the square shape look like. If you use triangles instead, then the shape change is something like this. So here's the cross sections. At the end point, you'll actually have a square, a triangle that looks like that, and that's where the green shape is defined by. So using equilateral triangles, the shape is going to look like this, whereas, and we'll go ahead and put it over one more time, when you use squares, the shape look like this. So this time, you're going to want to find the volume of this green solid, and I think just to help you picture it, we'll go ahead and take that out. It'll look like this. So find the area, or pardon me, the volume of this solid using equilateral triangles as your cross-sectional sections. So we'll stick the grid back on, and in most books, sometimes they'll give you the outline of the final shape, this green shape here, and sometimes they won't. In most cases, you'll have something that looks kind of like this. You'll have the base, and you'll have a solid. So let's go ahead and solve the problem now, and we're going to do it exactly the same way we did last time. And let's go back, and again, if you haven't watched the first video, I'd watch it, but I would recommend this series of steps, and it starts out like this. The first two steps are to make a sketch that you can use to set everything up. Then the last three steps are to actually evaluate it. And eventually you're going to want to find this, is just find the cross-sectional area of whatever the shape is that you have in terms of x, multiplied by its thickness, which will give you the volume, and sum them up in an integral, and you'll have the volume of the whole thing. So the first one says this. It says, sketch the base of the solid in the xy plane using the boundary conditions. So let's go ahead and do that. Now back over here, just like in that first video, it's hard for some students to draw a three-dimensional system. So my suggestion is to always just go ahead and, let's put it over here, set it up as a three-dimensional system looking directly down on it from the top. And if you draw it like this, it makes it a little bit easier to do. So this is what I'm going to call the working sketch, which is what you'd have on your homework page. And this is what the book situation is going to look like. So first of all, let's run through our steps. So the steps say, sketch the base of the solid in the xy plane using the boundary conditions. And to do this, it's really just a matter of doing this. First of all, you've got the graph of x is equal to y squared, which is just a parabola that's symmetric about the x-axis. So just go ahead and sketch that on your sheet, and it'll look something like this. Then it's open at this end, so to restrict it, you'll put the line x is equal to 4, which is a line perpendicular to the x-axis, and go ahead and put that on, and it'll look like that. Now when you do that, that actually gives you the shape of the base, and it looks like this, which is what this situation is over here. So on your sheet of paper, just make a quick sketch of this. Now, as far as sketching the cross-sectional area, and actually let's go back to our steps again, you've now completed step 1. You've got a sketch of the base. So going to sketch 2, or step 2 says sketch a single cross-section in the required geometric shape. So what we're going to do is go back to our little sketch here, and we're going to sketch a single equilateral triangle. And this is what it looks like in 3 dimensions. And to do this, you actually did this. You came over and started with a baseline right here that formed the base of the object. And we'll do the same thing on this thing. We'll go up, and I think I'll go in some distance x and say right about from here, and I'll go down to here. So there's my baseline. Now, in the book sketch, it looks like this. On our sketch, we'll do the same thing. We'll sketch a triangle. And again, just fairly rough sketch. I'm going to take it, say, from here to here, down to here. And I also would like to sketch a little thickness to it. So I'm going to go from here to here and down to here. And I'll show it going like this, and say from here up to here. Okay, and then I tend to just shade this a little bit just to remind me that it's not a plane, it's actually an object that has some thickness to it. And again, the thickness of this is going to be dx. So that's going to be the thickness of that triangle. Just like over here, the thickness was dx. So now, I've got step 1 finished, which was to draw the base. I've got step 2 finished, which is to draw a representative cross-section. And let's take a look at the next step. So now, the next 4 steps are all just solving the problem. Now, to solve the problem, you've got to get the cross-sectional area in terms of x, but you need to start with a general formula for whatever the area is of the shape that you've been given, in our case, an equilateral triangle. So let's go back, and we'll go ahead and write those down as we go. I think I'll put it right about here. So what I want is to start with a general formula for the area of an equilateral triangle. And if you dig out one of your old geometry books, you'll find that the area of an equilateral triangle would be equal to, and it's the square root of 3 divided by 4 times whatever the side is, so the side of the triangle squared. So this is the general formula for the area of an equilateral triangle. Now what you have to do in the next thing, let's go to the next step here. The next step says find the area of that single cross section, but this time rather than a general formula, you have to set it up specifically according to your figure in your problem. So this is the general formula. So what we're going to do is this. First of all, I need the side. Now the side, and on my sketch, it's going to look like this. From here to here, that is the length of the side. So what is it in general terms by your figure? Well, again, if you come in this distance x, if you go up this distance y, then by my figure, this height from here to here would be y. Now, by symmetry, these two are symmetric, so if this length is y, then this length from here to here would also be y. So the total length of the side from here to here would be y plus y, or 2y. In the way I've got my figure set up, that's going to be the length of a side in terms of my figure. So now, go back to your general formula and replace the side with what you know it is. So this would be square root of 3 divided by 4. And now I know that the side is, each side is 2y, and that's squared. So go ahead and square both things in there. You get square root of 3 divided by 4. And when you square the 2, you get a 4, and you get y squared. And then on this problem, the 4's will cancel out, so that cancels out with that. And you wind up with the square root of 3 times y squared. And what this is the area, with one exception. This is the area, but it is in terms of y. So you've got this area here. This is the area in terms of y. But that's going to be a problem. Let's go back and look at our steps again. Now, you've got the area in terms of y, but to do the integral, you can't solve the integral unless everything in there is in terms of x. So you need to, in the next step, change the cross-sectional area from an area in terms of y to an area in terms of x. So how do you do that? Well, let's go back to our picture, and it actually has to do with like here. Is look back up at your boundary conditions. So way back up at the top of the problem, in the boundary conditions, you were given that x is equal to y squared. So start with that and use that to help you convert this thing. So to change it, if I know that if x is equal to y squared. Take the square root of both sides, and you'll get the square root of x is equal to y. Now you can use that back over here. So the area in terms of y was the square root of 3 times y squared, but in place of y squared, you're going to put what y is equal to, which is the square root of x. So this would be the square root of x, and then quantity squared. And what this is going to give you is the square root of 3, and then the square root of x squared, the square root cancels out, and it just leaves you with x. And what that's going to be the area of that cross-section in the shape of an equilateral triangle, but finally you've got it in terms of x. So from your picture, you had to get it in terms of y, but then just change it from a formula in terms of y into a formula in terms of x, and this is what you're going to put inside the integral when you graduate to formula. So again, now let's go back and look at our steps. So we finished step 4. You've got the area of a single cross-section in terms of x. So the next thing you need are the limits of integration from what to what, and again, you can get that off your figure, so let's go back and look at the figure. And what that's going to be is this. dx is the thickness of the rectangle, so you're going to integrate it from here over to here. So this is going to be, and you can tell this also if you go back up and look at your original boundary conditions, this goes from x equal 0 right here, and it goes over to right here. And this is going to be x is equal to 4, and you know that because of this equation up here. So those are going to be the limits of integration. And now it's just a matter of, and we'll go back to our steps again. Step 6 says evaluate the integral from a to b. You know the cross-sectional area of each equilateral triangle in terms of x, and the thickness of each triangle is dx. So finally, let's just plug it all in. It's just a matter now of evaluating the integral. So if we go down to here, you've got the volume is going to be equal to the integral from x equals 0 to x equals 4 of the cross-sectional area in terms of x, but that is the square root of 3 times x, and then dx. And that's just strictly this formula right here. So the volume is from a to b, cross-sectional area in terms of x times dx. And now it turns out to be a fairly simple integral to evaluate. So we'll go ahead and move the square root of 3 outside the integral sign. You're going to go from 0 to 4 of x dx. So x dx. And we'll go ahead and put that down here then. That's going to be the square root of 3. And this will change into x squared divided by 2 when you take the antiderivative. It goes from 0 to 4. And when you plug in the 4 and the 0, you would get the square root of 3 times 4 squared divided by 2 minus, this will be 0 squared divided by 2, which is going to give you 16 divided by 2, which would be 8, and the final answer then would be 8 times the square root of 3. And what this is the volume of that green solid exactly. And if you stuck that on a calculator and changed it into a decimal, I got 13.86. And this would be cubic whatever the units are, so 13.86. So that takes care of the problem. Let's go back up at the beginning. So 13.86 is, and again, just to show you what you've actually got for a final answer, if you were to put that on there and remove this axis here, is 13.86 is the volume of this green solid right here using cross-sectional steps. So again, real quickly, let's run back through our steps one more time. And the step says, first of all, just sketch the base of the solid in the XY plane and sketch a single cross-section. And my suggestion would be just to go ahead and use a working sketch for this on your page. If the book happens to give you a sketch, great. But again, just for your homework, it's easier to draw if you just draw it looking down from the top. So there's the base, there's cross-sectional area. Then to actually find the integral, it's just a matter of starting with a geometric formula, change it into a specific formula for your picture. So in our problem, the initial formula for, in general, for an equilateral triangle, just start with that and find that in a geometry book. Now change it from side squared into whatever it is for your picture. And in this case, first of all, I had to change it into an area in terms of y. Then you need to get the cross-sectional area in terms of x. So use the boundary conditions up here at the top to change it from a formula in terms of y to a formula in terms of x. And then finally, as you get down to the bottom of it, the last part's not too bad, is just going back to your things, find the limits of integration, put it in the integral, evaluate the integral. And in our case, the actual integral turned out to be fairly easy to evaluate. So it'll give you this. So anyway, there's the steps. And again, starting from your picture, if you draw a working sketch that looks like this, from the working sketch, you should be able to get everything that you need to plug in the formula. So that was a sample. The first video used this problem with square cross sections. This second video used equilateral triangles, and I think what we'll do in the third video is use semicircles, just to give you some variations on this. So semicircles in the next video.